The atomic theory proposed by John Dalton stated that atoms are indivisible. This idea was proven incorrect by the end of the 19th century, when it became clear that atoms are actually composed of several basic types of particles. The number and arrangement of these particles determine the properties of the atom. The atom is now defined as the smallest particle of an element that retains the chemical properties of that element. Atoms consist of two regions. Each region contains different types of particles, called subatomic particles. One of them is the nucleus, which is a very small region located at the center of an atom. The nucleus includes at least one positively charged particle, which is called a proton, and usually one or more neutral particles called neutrons. Surrounding the nucleus is a much larger region that contains negatively charged particles called electrons. First main idea. Atoms contain positive and negative particles. The electron was the first subatomic particle to be discovered. In the late 1800s, many experiments were performed in which electric current was passed through various gases. Now, a gas with the same pressure as the air at Earth's surface is a poor conductor of electricity. For that reason, the scientists made sure to keep the gases in their experiments at very low pressures. For their experiments, scientists made glass tubes called cathode ray tubes and filled them with low-pressure gas. Metal discs were placed on either side of the tube. One disc, the cathode, was given a positive charge. The other disc, the anode, was given a negative charge. Cathode rays and electrons. Scientists discovered that the surface of the cathode ray tube glowed when electric current was passed through the tube. They hypothesized that the glow was caused by a stream of particles, which they called a cathode ray, which traveled from the cathode to the anode. They also found that cathode rays could be detected by a magnet or away from a negatively charged object. This led to the hypothesis that the particles in a cathode ray are negatively charged. Experiments carried out by English physicist Joseph John Thomson in 1897 supported this hypothesis. He was able to calculate the ratio of the charge of the particles to the mass of the particles in a cathode ray. He found that this ratio was the same no matter what metals were used in the cathode and anode. The ratio also stayed the same if the gas in the tube changed. Thomson concluded that all cathode rays are composed of identical, negatively charged particles, which we now call electrons. The atoms in the cathode ray experiments release electrons. This was evidence that atoms are divisible and that electrons are present in different types of atoms because of the different metals and gases used in the experiments. Charge and mass of the electron. Thomson's experiments also revealed that the electron has a very large charge-to-mass ratio. In 1909, the American physicist Robert A. Millikan was able to measure the charge of the electron. Scientists used this information to determine the mass of an electron. They found that an electron has about 1/2000th the mass of the smallest known atom. Thomson proposed the plum pudding model to explain the properties of the atom known at the time. Because atoms are electrically neutral, he proposed that the electrons were balanced by a pudding, or a matrix, of positive charge. The electrons were embedded into this positively charged material. The region of positive charge was also thought to contain most of the mass of the atom, since the electron had so little mass.
When the cathode and anode of a cathode ray tube are connected to a voltage source, electric current flows through the tube and can be seen as a cathode ray. The cathode ray is made up of electrons. When a positive electric field is placed next to the tube, the path of the electrons moves toward the field. Using the strength of the electric field and the amount of deflection, J.J. Thomson was able to calculate the ratio of the charge of electrons to the mass of electrons. Imagine a baseball player throwing a ball. Like the cathode ray, with no outside influences, the ball goes straight when the baseball player throws it. A strong wind, however, could blow the ball and make it go off course. An outside positive field attracts the electrons in the cathode tube and makes them go off course. If the baseball player threw a lightweight plastic ball instead of a regular baseball, the wind's effect would be even more evident. The mass of the ball is one of the factors that determines the path the ball will take. Similarly, if the wind were stronger and the baseball player used the original ball, the wind's effect would be more evident. The strength of the outside force is one of the factors that determines the path the ball will take. By observing the path of electrons in the cathode tube, Thomson was able to calculate the ratio of charge to mass of an electron. In Millikan's oil drop experiment, he squirted negatively charged microscopic droplets of oil into a chamber and observed them with a microscope. Voltage applied to metallic plates within the chamber allowed him to create an electric field, which had an effect on the droplets. By adjusting the electric field's strength and direction so that it pushed the droplets against gravity, he could suspend the droplets. By knowing a droplet's mass and the strength of the electric field needed to suspend it, he calculated its charge. Testing several droplets in this way, he found each droplet's charge to be a whole number multiple of 1.602 times 10 to the negative 19 coulombs. This is the charge of an electron.
Second main idea. Atoms have small, dense, positively charged nuclei. More detail of the structure of atoms was discovered by New Zealander Ernst Rutherford and his associates Hans Geiger and Ernst Marsden. They bombarded a piece of gold foil with fast-moving alpha particles, which are positively charged particles with 4 times the mass of a hydrogen atom. They expected the beam to pass through the foil with very little deflection because the mass and charge were unevenly distributed in the gold foil. They were surprised when 1 in every 8,000 alpha particles deflected backwards toward the source. Based on this, Rutherford hypothesized that small, densely packed bundles of matter with a positive charge must have caused the backwards deflection. The bundles had to be small because so few of the particles bounced backwards, only 1 in every 8,000. Rutherford used the term nucleus to describe each bundle of matter. Rutherford had discovered that the volume of the nucleus was very small compared to the total volume of an atom. The source of the positive charge of an atom had been discovered. Rutherford's student, Niels Bohr, later discovered the location of the electrons in an atom. Rutherford reasoned that each atom in the gold foil contained a small, dense, positively charged nucleus surrounded by electrons. A small number of the alpha particles directed toward the foil were deflected by the tiny nucleus, which on the screen here is represented by red arrows. Most of the particles, however, passed through undisturbed, on the screen here represented by the black arrows.
Ernst Rutherford, with Hans Geiger and Ernst Marsden, discovered the nucleus of the atom using a beam of positively charged alpha particles. They bombarded a sheet of gold foil with a stream of alpha particles. Most of the particles passed straight through the foil. About 1 in 8,000 particles, however, were deflected, sometimes directly back at the source. Rutherford explained these results by hypothesizing that nearly all of the mass of an atom is concentrated in a very small volume called the nucleus. If the nucleus were small, it would be easy to miss. Alpha particles which miss the nucleus are deflected only slightly, if at all. Alpha particles which hit the nucleus are deflected severely.
Third main idea. A nucleus contains protons and neutrons. With one exception, all atomic nuclei are made of two kinds of particles, protons and neutrons. A proton has a positive charge equal in magnitude to the negative charge of an electron. Atoms are electrically neutral because they contain equal numbers of protons and electrons. A neutron has no charge and, like an atom, is electrically neutral. The one atomic nucleus that lacks a neutron is that of the simplest hydrogen atom. Its nucleus is a single proton with a single electron moving around it. A proton has a mass of 1.673 times 10 to the negative 27th kilograms, which is 1,836 times greater than the mass of an electron. Therefore, a proton has nearly all the mass in the simplest hydrogen atom. The mass of a neutron is 1.675 times 10 to the negative 27th kilograms, which is slightly larger than the mass of a proton. The nuclei of atoms of different elements differ in the number of protons they possess. Therefore, the number of protons identifies an atom's identity. For every proton an atom has in its nucleus, the same number of electrons surround the nucleus. Physicists have discovered other subatomic particles, but they have very little effect on the chemical properties of matter. The properties of electrons, protons, and neutrons are summarized in the table on the screen now. Please pay special attention to the relative electric charge as well as the mass number. Forces in the nucleus. Generally, particles that have the same electric charge repel one another. Therefore, you might expect a nucleus with more than one proton in it to be unstable. However, a force exists between two protons that overcomes the electric force trying to push them apart. This force only acts when two protons are very close to one another. A similar force acts when two neutrons are very close together, or when a neutron and a proton are very close together. Together, these short-range proton-proton, neutron-neutron, and proton-neutron forces are called nuclear forces. These forces allow atoms with up to 83 positively charged protons in the same nucleus to be stable. Fourth main idea. The radii of atoms are expressed in picometers. Because the nucleus is so small, the size of an atom is determined by the size of the region in which electrons are present. This region is sometimes thought of as an electron cloud, meaning a cloud of negative charge. The radius of an atom is the distance from the center of the nucleus to the outer edge of the electron cloud. Because atomic radii are so small, they are expressed in a unit that is more convenient for the sizes of atoms. This unit is called the picometer. Another unit, called the Unified Atomic Mass Unit, or U for short, is used to express the mass of atoms. 1 picometer is equal to 10 to the negative 12th meters, which is also equal to 10 to the negative 10th centimeters. And 1 U is equal to 1.660540 times 10 to the negative 27th kilograms. To get an idea of how small a picometer is, consider that 1 centimeter is the same fractional part of 1,000 kilometers, which is about 600 miles, as 100 picometers is to 1 centimeter. Atomic radii range from 40 picometers to 270 picometers across. Atomic nuclei have much smaller radii, which is about 0.001 picometer. Atomic nuclei are also incredibly dense, with a density of about 2 times 10 to the 14th grams per cubic centimeter. At this point, you should be able to summarize the observed properties of cathode rays that led to the discovery of the electron, summarize the experiment carried out by Rutherford and his co-workers that led to the discovery of the nucleus, list the properties of protons, neutrons, and electrons, and then define atom.